Hey there, it's me, Miss B. And in this video, we're looking at the Unit 5, Lesson 9 practice problems for Illustrative Math Algebra 1. So let's dive in. Okay, we have the number of people with a flu during an epidemic, and that's going to be a function f of the number of days since the epidemic began. So the equation f of d equals 50 times 3 over 2 to the power of d is what defines function f. So how many people had the flu at the beginning of the epidemic, and explain how you know? Well, at the very beginning of the epidemic, we are going to use our initial value of 50. So 50 people. We can say because that is, we can just call it the initial value. We can also say that the function, when you input 0, will give you 50. So both of those are true. When we input 0, anything to the power of 0 is 1. So that means right up here where we're saying 3 over 2, if we're raising it to the power of 0, it becomes a 1, and we just multiply and have our 50. So that is going to be our initial value, but it's also the value when we input 0. Either of those are good explanations. Now, for part B of this question, how quickly is the flu spreading? And explain how you can tell from the equation. So they're asking us to look at our growth factor. The number of people with the flu, how quickly is that spreading? Well, it's 3 over 2, so it's not quite doubling, but each day, 1.5 times the number of people have the flu as the day previous. So it's like they're adding, on top of what they already had, they're then adding another like 50% of people. So instead of every single person passing it to one more person, it's like half of the people are giving it to one more person, but that's still a lot, and they can still grow really fast. So let's actually put an explanation for this. How quickly is the flu spreading? It spreads. Don't want to say it spreads fast enough. Yeah, we can say it spreads so that 1.5 times the number of people um, uh, have the flu. That flu does not have an E on it. Have the flu each day. But then I'm also going to put my secondary explanation is that I can say it spreads, or oh, it was the number of people. That's right. So half, because we're growing by half. So yeah, I can say each half of everyone sick spreads it to another person. Because ultimately, if I'm trying to explain how it's growing, it's not that every single person is, it's just that half of everyone who's sick is spreading it to another person, and this is each day as well. Okay. Now I'm actually gonna put myself a little line here because I don't want it to look like that's my answer to part C. So that way I can keep my answers apart. I'm also just going to do part C in red. So it says, what does f of 1 mean in this situation? And so we don't have a graph that we're supposed to be reading this from. We're just trying to determine what it means. So we can say this is the number of people with the flu on one day after it began. It was difficult to say on the first it's difficult to not say on the first day, because the first day where the initial value is 0, this is one day after. The flu one day after it began. Do we know how many people that is? No, they're just asking what it represents. We could plug it in and figure it out. Now they're asking, does f of 3.5 make sense in this situation? So they're really asking, hey, 3.5, is that okay for us to have as an input? And for this, I am going to say yes, because this is days and we can measure in partial days. It's 3.5 days after it began spreading, and that is a perfectly acceptable number to use as our input. So yes, I'm going to say it would represent. I'm just going to describe what it represents because you can then logically conclude that it makes sense. It would represent the number of people with the flu 3.5 days after it started spreading. Okay, let's move to question 2. So for question 2, we have the function f gives the dollar value of a bond t years after the bond was purchased. And so the graph of f is shown. We have the value in dollars along our y-axis, and then along the x-axis, or the horizontal axis, we have the time since purchase. So they're asking us to analyze a couple things here from this graph. What is f of 0? What does it mean in this situation? Well, f of 0 means look here and find this number, and that is going to be the amount of money that the bond was purchased for. So we can say f of 0 equals, and this is 1,000, which is how much the bond was purchased for. Like when they bought it, that's how much they bought it for, and that's how much it was worth. Now let's look at B. B is what is f of 4.5, and what does that mean in this situation? So 4.5, that is in years since purchase. So 4.5 is right around here. Let's zoom in here so I can actually look. So we would have 1, 2, 3, 4.5. Yep, so right around here. And this puts us right around this spot. And I believe these are counting by 100. So 1, 2, 3, 4, 5. Yep. And that puts us right around 1,250. This would be 1,100, 1,200, 1,250, right around there. I can say f of 4.5 And since I'm reading from a graph, I'm going to put the approximate sign or my wiggly equal signs because we're not entirely sure since it doesn't give us an equation for this. So 4.5 is approximately 1,250. And we're going to say it's the value of the bond after 4.5 years. That's just how much it was worth after 4.5 years. So for the last part of this question, they're asking when is f of t equal to 1,500, and what does that mean? So now we're not actually looking at our time to start with, we are looking at our value in dollars. So 1,500 or 1,500, that is right about here. So I'm going to actually put a red mark there. We'll put a red mark here. And if we draw this number down to read how many years, it's not quite 8.5. It looks more like 8.25 or 8.3. I'm going to just round it to 8.25. So I can say, I'll say f, oops, not in red, f of t equals 1,500 when t is approximately, because I am estimating, and I said it was around 8.25, and I can say the bond was worth $1,500. About 8.25 years after it was purchased. And there we go. Really just giving context of what those numbers mean is what this one was asking us for. So let's now look at question 3. All of the students in a classroom list their birthdays. Is the birth date a function of the student? And then we have the opposite question, is the student a function of the birth date? So when they say blank is a function of blank, that would mean they're asking output and input. Because a function statement would say output is a function of input, so they're asking us if this works. Now, if I input the student's name and it outputs a birthday, no student is going to have 2 different birthdays. So yes, there is one input for one output. So yes, one student would give one birthday. Okay, but now the other direction they're asking is the student, so looking at the student as the output, a function of the birth date, which would be the input now. So they're asking for output and input here. So that means if I am inputting a birth date, it would output a student's name. And because people can share birthdays, this is not necessarily a function. So we would say no 2 students can have the same birth date. And that's it. It is not always going to be a function, so my answer for this will be no. although you could make it a little situational and say, if two students have the same birthday, then it's not. But since it's not always going to be, I just like to default to no, because we can't count on it to always be a function here. So that's the first half of this assignment. Let's look at the back side. So this one says technology required. So we are going to be looking at some approximate values. Now, my class specifically, we didn't answer some of these questions like part D. So if you are in my actual class, then you do not have to answer for D, but I will answer it with the rest of you. So technology required. A function f gives the number of stray cats in a town t years since the town started an animal control program. The program includes both sterilizing stray cats and finding homes to adopt them. So an equation representing this function f is f of t equals 243 times 1/3 to the power of t. So what is the value of f of t when t is 0? So when t is 0, if we plug in 0, we get 243, just whatever our initial value is. F of 0 is 243, and we can say this is the original amount of stray cats. So this is the original amount of stray cats. There we go. What is the approximate value of f when t is 1/2? And explain what this value means in the situation. Well, I am going to actually plug this in on Desmos, the graphing calculator, because I'm going to have to graph it anyways. But we can actually first plug into the equation the approximate number. So I'm going to use my scientific calculator first. 243 times 1/3, and we're going to raise this to the power of 1/2. So I'm going to open up my scientific calculator here. 243 to the times 1/3, and we are raising this to the power of 1/2. Now the answer appears over on the right, so that is 140.296. So 140.3, or we'll just say around 140. So let's go back to our notes here and say f of 1/2 is approximately 140. Now explain what this means. This is, well, t is in years. So if t is 1/2, that means half a year. And this would be the population of stray cats after about half a year. So there are about 140 stray cats after half of a year. Okay, now for part C, they said, what does the number 1/3 tell you about the stray cat population? Well, first off, it tells me that it's decreasing. So it sounds like the city's program is working, or town, to call it a town, sorry. And it tells us that there is only 1/3 of the population left each year. So the population of stray cats is Now, we could say it's decreasing by 2/3 each year, and that would be sort of like the 1 minus 1/3 idea. So that's what I am going to describe this as, just because the English sentence sounds best as a response to this question. So the population of stray cats is decreasing by 2/3 each year. Okay. Now it says use technology to graph f for values of t between 0 and 4. And what graphing window allows you to see values of f of t that correspond to these values? So let's go with our original equation here. And I am going to move over to the Desmos graphing calculator, which is different. And I'm going to plug this formula in. So we'll say f of t is equal to, and this was 243 times 1/3, and we're going to raise this to the power of t. Okay, so now I have a function, but centered at 0, 0, and going from -10 to +10, I can't see a whole bunch. So it is asking me for my input values of 1 through 4. So I really just want to see years 1, 2, 3, and 4 here, and that's on my x-axis. But when I zoom in equally, it doesn't quite show. So what we're actually going to do is shrink the y-axis here, or the vertical axis. And I'm going to do that with my touch screen, because this is my tablet. I am going to do that until it actually shows up on my screen. So I'm going to squish it down this way, and we will see. Our starting number is 243, so I at least want to include that. Maybe 250 is a good place to start. So yeah, using graphing technology here, I could use my window at 0 at the bottom, but I at least want to go up to 250. And then I don't have to really go much further than 4, because if I go further than 4, it just gets very, very small, and it's really, really hard to read. Plus, they only wanted values of 4 to fit in our window anyways. So I'm going to say that my window should be between 0 and, we can maybe say 4 or 5 on the x-axis, and 0 to 250 on the y-axis. Now, I did mention that for students in my class, I did not ask you to do a bunch of questions like this. We did talk about what part of the graph makes more sense, but we've kind of avoided the graphing thing. So if you are in my class specifically and you feel a little bit lost, that's okay. So what graphing window allows you to see that correspond to these values of t? So I'm going to say on x, I need it to go from 0 to 4 is nice, but like 4, or I can say 0 to 5, something like this. On my y-axis, it was easiest to go from 0 to 250. And we can say or similar. We don't need to go much higher than that, because our numbers will not be on the screen. And so that is all of question 4. Let's take a look at question 5. Question 5, we have function g giving the amount of chemical in a person's body in milligrams t hours since the patient took the drug, and the equation g of t equals 600 times 3 over 5 to the power of t is what defines this function. Okay, so they said, what does the fraction 3 over 5 mean in this situation? And then they want us to sketch a graph of g. So we will sketch, and then we're going to talk about the domain and the range of G and what they mean. So we have G representing the chemical, and T representing the hours, 3/5. So 3/5 is the growth factor here. So when it is decreasing like this, because that number is less than 1, it represents how much is left after each interval. And so for us, that is 3/5 of the original dosage. Each hour is what's left. So we can say 3/5 of the chemical is left each hour. Okay, and so if we want to sketch a graph of G, I'm going to use my black marker to do this. Technically, I want to know when it would become 0, and if you have a chemical left in your body, it should eventually become 0, but since this is exponential, our exponential values are never actually going to reach 0. But I might zoom in here and say, like, yeah, up here is going to be 600, and so at 600, I know I'm going to have a point, because it should be decreasing. Now this down here, I'm sorry, is going to be hours, since it was taken, and this would be chemical in milligrams. Okay, so after 1 hour, 3/5, that means we would take 600 and multiply it by 3/5, or if it works better for you, you can take 600, divide it by 5, and then multiply that by 3. Either way, for both of these, it would give you 360. And 3/5 is just a little bit over half. So that kind of works for us. So if this is 6, this would be 3. So 4, 5, and 2, 1. Let me label all of my bars here. That way I can actually estimate where 360 is at. So it's going to be just a little bit over 350. I'll put it maybe like here. So let's say this is 1 hour, and then we'll have like 2 hours, and then I'll kind of just sketch from there. So at 1 hour, it was 360. So that would put me right around here. And then if I took 360 and I did the same thing, I'm just dividing by 5 and then multiplying it by 3. That is 216 at 2 hours. So it looks like it's just going to decrease by a little under half. And so I'm going to actually use a red line to kind of just show my sketch of what this probably looks like. And as long as I follow through those points, it should be pretty accurate, but I am going to make them a little darker just to emphasize that, like, hey, I actually calculated those. But it does say sketch, so it doesn't say make a very precise graph. But now we want to talk about domain and range. So the domain and range of G. Domain is going to be hours, since the patient took the drug. So I can say domain, and the best way to describe this domain, I mean, technically the domain of this could go on forever. So I could say that it's where x is greater than or equal to 0, because I'm just going to have x values, or horizontal axis values, literally bigger than 0. And it is allowed to be fractions, it's allowed to be partial numbers. That's fine too, because we're measuring time. Now for range, we are going to have a bottom amount, because our minimum here is going to be 0. but our maximum here is going to be the 600. So my range, if we consider range to be y has to be less than or equal to 600 because they took 600 milligrams and it's going to decrease over time. But technically, according to this, it's going to be greater than 0. Because mathematically, it's never actually going to reach 0, even though it might realistically in the patient. If you want to include the equal to underneath, that's up to you. I would argue that it should stay like this. So domain, I'm going to describe what they mean. The domain is the hours since the patient took the drug, or just all the possible values for the number of hours, and then the possible amount of chemical in the patient's body, or they said the person, in the person's body. Okay. And that is going to be it for number 5. Let's look at question 6. And then we have another question back here, number 7. So we are going to keep going. I thought for a second that this was only front and back, but it's more than that. So the dollar value of a moped is a function of the number of years t since the moped was purchased, and the function is defined by f of t is 2,500 times 1/2 to the power of t. What is the best choice for the domain of the function? So domain always talks about input, and for us, that is going to be the number of years since it was purchased. So number of years. If it was, well, hold on, I'm going to stop myself there real fast. I like to ask myself a couple questions when I'm asking about, do certain numbers make sense? So I always like to think, can I use 0? Can I use negatives? And can I use fractions? So in this case, if it's years since the moped is purchased, I can use 0. If it's years since the moped is purchased, it doesn't really make sense to use negatives, because if it's brand new, then it's not going to have increased in value if the moped doesn't exist yet. So I'm not going to include negatives, and then I am going to use, I am going to allow 0 to work, so that narrows me down to 2 choices. Not going to use negatives here, so not going to use A and B. I am going to use 0, so 0 works for both C and D. But now the question is, do I use 10 or do I use 100? And it said the number of years since the moped was purchased. Well, I'm going to guess that 10 years is more reasonable than 100 years. So we can say 10 is more reasonable than 100 years. So it is highly unlikely that we're talking about this moped 100 years after it was purchased. And if it's in very good condition, I highly doubt that this would actually stay. It would probably go up in value after it became super, super old and antique. So yeah, we're going to go with 0 to 10. So that's it for 6. We're going to flip over to 7 and 8, and then we are going to be done. So this is another person with, in this case, it is milligrams of medicine, and they are a patient instead of just a person with a chemical. But the same idea applies. So each hour, 1/5 of the medicine in the patient's body decays. So that means 1/5 disappears. So 1 minus 1/5 means that 4/5 is left. That's what I think about initially before even reading the rest of the question. Now, part A here wants me to complete the table with the amount of medicine left in the patient's body. Well, good thing I just figured out what my growth factor should be, because that is what we are going to do. So hours since receiving the medicine, they are 0 hours. They're going to have 1,000 milligrams. That's the initial dosage, the initial value. So after 1 hour, if we took 1,000 and we multiplied it by 4/5, or in this case, divide by 5 and then multiply by 4, that's going to give us 800 milligrams. And if we did that again and multiplied it by 4/5, that would give us 640. One more time, if we multiply by 4/5, we will get 512. Now, if we had h, this is where it's asking us to really kind of build a function here. So our pattern is that we are taking the 1,000 and we are multiplying it by that 4/5 every single hour that passes. So that's going to be my equation, m. And I like to write these in function notation, m of h, because medicine based on the hours helps me recognize what's the input, what's the output. So m of h equals 1,000 times 4/5 to the power of h. Okay, now use your equation to find m when h is 10. So I'm going to do this on a scientific calculator, but off screen you don't need to watch me do it, but we are going to actually input these numbers. So I would like you to double check that you can enter this into a calculator yourself as well and get the same result, because you always want to make sure you're capable of doing those things as well. So I'm entering in 1,000 and then in parentheses my 4/5. And then instead of this h right here, we are using the power of 10. And my equation tells me that the medicine after 10 hours is, and I am going to round this a little bit so I can even put my little approximation, or I'll just round it off. But it is 107 point, I'll go with 37. I like to go 2 digits after the decimal place, and we'll say milligrams. So what does this mean? This means 107.37 milligrams is left in the patient's body after 10 hours. There we go. Okay, that's question 7. Now let's look at question 8. We have trees in a forest and they're suffering from a disease. Oh no. The population of trees, P, in thousands, is modeled by the equation P equals 90 times 3/4 to the power of T, where T is the number of years since 2000. So they want us to find the tree population in 2001 and then in 1999. So I'm going to put this for myself in terms of how they want us to think about things. So T, or my value of T here, is not just the year, but it's years since 2000. So if they said 2001, that is when my time is 1 year. But if they say 1999, I actually am going backwards in time, so I'm going to have to say -1. So we're going backwards in our analysis here. And I'm just gonna plug these numbers into my calculator. So let's do that. We'll use 90 times 3 over 4, and we'll raise that to the power of 1, which is going to be 67. We'll say the population in 2001 was, and then this is 67.5. And this is in thousands, so we're allowed to use fractions because they're measuring this in thousands. And we can say now the population in 1999 was, and I am going to go back to my calculator and input here a -1 as my exponent, and this gives me 120, which would make sense because that is bigger than 90. So if we're going backwards, we should be growing, because going forwards, this tree population in this forest is shrinking. So what does the number 3/4 in the equation tell you about the population? It tells us that only 3/4 of the trees survive each year. Or you could say that it means that 1/4 of the trees in the forest die from that disease each year. Either way, but when possible, I like to just use the number itself instead of the 1 minus version. Okay, now we want to know what is the last year when the population was more than 250,000. So remember, our equation gives us our answer in thousands. So we want to know the population over time. We want to know when that was going to be greater than 250, because our answers are given in thousands. So we can keep going backwards and find out when that happened. So we put in -1 and got 120. If we put in -2, we'll get 160. We can keep going backwards. So I'm going to make a little table, maybe even off to the side, and just say that this is going to be t, and then the population at t. So I said -1 was 120, -2 was 160. Let's do -3. This is 213 and 1/3. -4. This is 284. 0.4, and the 4 just repeats. I don't remember how to write that as a fraction. It might be like 4/9, something like that. Yeah. So what does -4 actually mean in terms of years? So we would basically just take 2000 and -4. So 2000 -4 is 1996. So we can say the last year that the population was above 250,000 was 1996, because I can say, no, it's P. I was about to write FP of -4 is 284.4, and P of -3 is 213 1/3. And this one was 1997. This one was 1996. There we go. Okay. And so, yes, there is not more homework questions after that. It does only go through 8, so it was 3 sides of a page. So I appreciate you sticking with me. But this was the Unit 5, Lesson 9 practice problems for Illustrative Math Algebra 1.